Hey everyone, let's dive right into this explainer. Today, we're going to discover exactly how computer engineers build artificial intelligence using an architecture that is surprisingly cute, but absolutely incredibly powerful. If you've ever wondered how on earth we went from staring at messy spreadsheets to having fluid, completely natural conversations with machines, well, you are in the exact right place. We're going to break down the actual engineering secrets behind large language models and show you the exact blueprint used to create them.
Here's a quick look at our agenda for today. 1. The Data Overload Challenge. 2. Meet large language models. 3. The Secret Recipe, RAG. 4. Retrieving the right information. 5. Generating the final answer. And finally, 6. Evaluating AI performance.
All right, Section 1, the Data Overload Challenge, why we needed better tools. So, before we even talk about advanced AI, we have to understand the fundamental problem computer engineers were wrestling with in the first place, which is extreme information overload. Imagine dealing with massive datasets packed with just way too much detail. You're looking at millions of rows tracking time, categories, locations, people. It simply has way too many dimensions. Trying to analyze this manually requires far too many repetitive steps. It makes it incredibly hard to see the big picture patterns, and ultimately it yields really slow and inconsistent results.
I mean, early solutions obviously involve spreadsheets, but manual data entry is just a total nightmare for consistency. Look closely at this date column, for example. We've got 26, 11, 13 sitting right next to March 23, 2016. Or check out the quantity column where someone literally typed the number 4 as a word. This mixing of text and numbers means that when engineers tried to run simple math formulas, the system would just crash and spit out those super frustrating #value errors. The data just wasn't standardized, which completely prevented basic filtering and grouping.
To fix this chaos, engineers leveled up. They started building business intelligence tools like Power BI to automatically load data from all sorts of diverse sources. They also used Python libraries like Pandas to efficiently handle those missing values and clean up the outliers. And this allowed them to transform that really messy data into beautiful, professional, and interactive dashboards that can automatically refresh and cross-filter.
Moving on to Section 2, meet large language models, the brains of the operation.
Now, dashboards are fantastic for visualizing past data, but to build systems that can actually think, converse, and generate totally new insights on demand, that's where engineers bring in large language models. At their absolute core, engineers build what are called foundation models. Think of a foundation model as a massive, super powerful brain that has ingested a vast universe of data. And we're not just talking text, we mean images, 3D signals, and speech. By processing all of this, the model actually learns the deep underlying patterns of human language and information.
And the true superpower of this engineering approach? It's adaptability. Because the foundation model has learned such broad patterns, it doesn't just do one specific thing. It can be adapted to do completely different tasks. So with just a little bit of tweaking, that single core model can be used for question answering, analyzing sentiment, extracting information, or even things like image captioning and object recognition. It's incredibly versatile.
The way we actually interact with these massive models is surprisingly straightforward. It's just a basic input-output loop. You give the LLM an input text, which we call a prompt. For example, you might ask it to write a Python function that receives an image and plots it using the matplotlib library. The LLM processes that prompt and generates a highly accurate, custom-coded output text response right back to you.
Section 3. The Secret Recipe, RAG, mimicking Google's Notebook LM. But here is a massive challenge engineers faced. An LLM only knows what it was trained on. So how do you get an LLM to answer highly specific questions about your own personal documents, like a company's private financial reports, or maybe your own study notes, without it just wildly guessing or making things up? Well, the ingenious solution engineers came up with is a secret recipe called Retrieval Augmented Generation, or RAG for short. This is actually the exact same architecture that powers tools like Google's Notebook LM. To make it really easy to wrap our heads around, we can visualize this RAG architecture as two cute cartoon roles working together, the dedicated sleuth and the creative storyteller.
The assembly line for this RAG architecture operates in 3 very distinct, highly coordinated engineering steps. First, we have context retrieval. Second, we package the prompt. And third, we call the LLM backend. Let's break down exactly how each of these steps works right now to create a genuinely smart AI application.
Section 4. Retrieving the right information. Enter the sleuth. Okay, step 1 is all about fact-finding. You obviously can't just feed a 500-page book into the LLM all at once. It's way too much context for it to handle. So when a user asks a query, like, say, were there any expansion plans in Asia, our adorable little water droplet, the sleuth, springs into action. The sleuth acts as a retriever. It uses semantic search to hunt down the most relevant chunks of your documents. It actually does this by converting the text into mathematical arrays called embeddings, and then rapidly searches through a specialized storage system called a vector database, like Quadrant, to pull out the exact paragraphs that contain your answer. Section 5. Generating the final answer. The storyteller takes over.
Once our sleuth has successfully retrieved those highly specific fact-checked document chunks, the AI assembly line moves right into step 2, prompt packaging. This is really where the magic happens. The retrieved facts are packaged into a very strict prompt template. It basically tells the AI, hey, given only the following context, answer the user's question. This carefully packaged prompt is then handed over to our storytelling cat, the LLM. And because the prompt is so strictly defined, the storyteller cat generates a totally natural, conversational answer using only the context provided by the sleuth. This completely eliminates any guesswork.
A really crucial point here for computer engineers is flexibility. The system is designed so that the storyteller isn't permanently hardwired. Engineers write a clever Python intermediate module, a function like invoke LLM, that allows the system to easily switch out its brain. Depending on their needs, they can seamlessly swap the backend LLM provider between a local Hugging Face model, Google's Gemini, or VLLM, all without having to rewrite the whole application.
Which brings us to Section 6, Evaluating AI Performance. Did the AI tell the truth?
Building the assembly line is one thing, but how do engineers actually know if their newly built AI is smart or just confidently wrong? Well, after the AI generates a response, it absolutely must be evaluated. Engineers constantly measure the system for two competing metrics, faithfulness and hallucinations. Faithfulness means checking that the AI's final answer strictly matches the facts retrieved by our sleuth. If the AI starts making up facts that weren't in the original documents, a phenomenon known as hallucination, engineers have to tweak the system. They combat this by adjusting LLM configuration settings, like the temperature, and by using stricter prompt engineering to just keep the storyteller in check.
And to objectively grade this performance, engineers don't just guess, they rely on math. The answer relevancy formula calculates a strict score between 0 and 1. It works by having the LLM actually analyze its own generated answer and dynamically create n number of possible reverse questions. It then calculates the mathematical similarity between those newly generated questions and the user's original query. A high score means the AI perfectly addressed exactly what the user was asking.
So knowing this entire engineering blueprint, you can now see that AI isn't just some inexplicable magic trick. From cleaning up messy data, to training massive foundation models, to deploying the clever sleuth and storyteller in a RAG architecture, it is just a brilliant, highly logical assembly line waiting for you to build with it. So what kind of intelligent tools are you going to build now that you know the secret recipe? Keep learning, and I will see you in the next explainer.